Hey Calculus, we are going to start Chapter 5, which will be on integrals, another main concept in calculus. So we're just going to review finding antiderivatives. Remember, to find an antiderivative, we're just going backwards. We are given f prime of x, the derivative, and we have to find the original function f of x. So this is a polynomial term here, so we're just going to undo the power rule to find the antiderivative. So instead of subtracting 1 from the exponent, we're going to add 1 to the exponent. So this is going to have to be an x to the 7th. So we have to ask ourselves 7 times what coefficient will give us a 7 out front. So that will be a 1. So our antiderivative function is x to the 7th plus c. The c represents a constant. That could be any number. And if I take the derivative of this, I end up with 7x to the 6th. Let's go to the next one. Okay, what function do we take the derivative of and get a sign? Well, it has to be cosine. But we know that the derivative of the cosine is negative sign, and we need a positive sign. So if we just put a negative 1 out front, that will come along for the ride, and you'll be set. Negative cosine of x plus c. To find the antiderivative of e to the 2x, this is a composite function. So I have to undo the chain rule. So first ask yourself, what do you think the outside function is? Well, it looks like the outside function here is e to something. And I think that the inside as is 2x. So I think that the inner function is 2x. So now, check. All right, take the derivative. Well, the derivative of the outer is e to something. The inner as is 2x. And the derivative of the inner is 2. So this right here, using this outer and this inner, gives me this derivative, 2e to the 2x, but I need 1e to the 2x. So what can I put in front to make that 2 become a 1? I can put in a 1/2. So if I put out a 1/2 in front, e to the something, and then my inner as is 2x. So there is my antiderivative. Here's a fun one. This is also a composite function, so we have to undo the chain rule. It looks like my outer function is something to the 7th. So when we're going backwards and taking the antiderivative, we have to add 1 to the exponent. So I think that my outside function is something to the 8th. And I think my inner as is 4x plus 5. So that's your first step. Figure out what you think the outside and the inside function is. Then check. Take the derivative. The derivative of this outer function is 8 times something to the 7th. The inner as is 4x plus 5. And the derivative of the inner is 4. So this outer and inner function give me the derivative 32, 4x plus 5 to the 7th. But I need a 1 out front right here. So what can I do to 32 to make it become 1? I can multiply it by 1 over 32. So that's my coefficient. 1 over 32. My outer function is something to the 8th, and my inner function is 4x plus 5. And then on the end of every antiderivative, I put plus c. Okay, there has to be an easier way to find antiderivatives other than going backwards in our head. All right, the fancy name in calculus for an antiderivative is an integral. So that's what we're going to do in Chapter 5. We're going to figure out what these antiderivative equations, these integrals, tell us and how we can find them easier than just going backwards in our head. Okay, so what is an integral and what does it tell us? An integral is the distance traveled, and we can find it by finding an area, specifically the area under a curve, under the curve between the curve and the x-axis. Let's look at this pretty easy example. I'm getting in my car and I accelerate along this graph. So the y-axis is our speed, our velocity. The x-axis is our time. So we accelerate to 60 feet per second. Okay, we know that distance is rate times time. So let's specifically look at the interval from 70 to 100. Okay, the time is 30 seconds. The rate is up here at 60 seconds. So if we take the rate, 60, times the time, 30, we get 1800. All right, and if we find the area of this section, the area of this rectangle right here between 70 and 100, we take the base, 30, times the height, 60. We also get 1800. Okay, so right here, let's read along. The area of the region under the graph also equals the distance traveled. All right? The process of evaluating this product in which one factor varies, in this case the y values vary, is how we find a definite integral. All right? And it has to do with the area. All right? So let's fill some of these things out. How is a definite integral different from an indefinite integral? All right, a definite integral has a left and a right endpoint. For instance, up here, our definite integral was between 70, the left endpoint, and 100, our right endpoint. All right, so a definite integral has a left and right endpoint. In order to find an area, we need a left and right endpoint to find a definite area. Okay, an integral tells us the distance traveled. All right, it tells us distance traveled. We find it by finding an area. Okay, what do we find? We find the area, specifically under the curve. All right, so how can we find area? There's lots of different ways in calculus that we find area. Think way back to the first time you ever found an area. Okay, the first way that we can find an area is we can count squares. All right, so let's look at example number 1. We have a graph of a rocket ship, the velocity, on the y-axis the time. We speed up and then we slow down. So, what calculus concept would you use to estimate the distance traveled? Distance traveled is an integral if we have a left endpoint at 0, which is right here, and a right endpoint at 8, which is right here. That is a definite integral. Okay, for number 2, we have to estimate this distance graphically. So we're going to count the number of squares in this region. All right, and I'm going to highlight it right here. So go ahead, pause the video. I want you to count the number of squares, and it's just going to be an estimate because there's partial squares up in here, but count the number of squares from 0 to 8. Okay, when I counted the squares, I kind of split it up into 4 regions, and there's a lot of different ways to do it, but my estimate, and again, it's a very rough estimate, the number of squares I got to be 75.8. So is that the area? No. Whenever you're finding the area, you not only have to count the squares, you have to keep track of the area of each little square. All right, so let's go up here, the area of each little square. You have to look at the scaling of your axes. Here we're scaling by 1s. All right, but the y-axis we're scaling by 20s. All right, so if we find the area of each square, the area of each square is 20 units. So we have to take the number of squares times the area of each square to get our area. So I'm getting an area of 1,516, and the units is miles. Now, how do we get units for a definite integral? You simply multiply your x units by your y units. Think about it. A definite integral is an area. Think area base times height. You multiply. So my x units are in minutes. That's up here, minutes. So we take minutes, and I'm going to make it a fraction because my y units are in a fraction. My y units along the y-axis are miles per minute. So my y units is miles per minute. All right, and if I multiply the fractions, these of course are going to cross off and I get miles. And that makes sense because it is a distance. So to get units for a definite integral, you multiply your x units by your y units. Okay, so there is our introduction to finding a definite integral. To find the area under the curve, counting squares. The next side of this note sheet, we're going to use rectangles, and then down the road, we will use those antiderivative equations to find definite integrals.